So we're going to do a problem using the central limit theorem, and this is a fun problem because it's dealing with kissing couples. And we're going to satisfy two objectives here. One, we're going to identify whether this is dealing with a sample proportion or a sample mean. And we're also going to talk about the concept of statistical significance. So there was a German biophysicist who wanted to know whether the fact that we have like right-handed and left-handed, or you kick with one foot or the other foot more than the other, your vision is more with one side than the other. He wanted to know whether or not that was something similar for whether people turn their heads to the right or to the left when they're kissing. So he observed couples, kind of like a voyeur here, a little peeping Tom guy. He observed couples from age 13 to 70, and he did it in public places like airports, train stations, beaches, in 3 countries: United States, Germany, and Turkey. So this guy's getting paid to fly all around the world to observe kissing couples. They did not include couples who were holding objects like luggage, because that could make a difference into which way you turn your head. And they observed a total of 124 kissing couples. Now, this 124, remember, so he's going out into the world and trying to find out something about all the kissing couples in the world, and he selected 124 of them to observe. So that is our N. Our N is equal to 124. That is our sample size. Now we're going to suppose that 1/2 of all kissing couples lean to the right. So we're making a hypothesis here. We're taking a guess. We're saying our hypothesis is that pi, the proportion of all kissing couples, that's why this all is such an important word. That's why it's pi is equal to 0.50. Now that is a parameter, that 0.50. Because we're assuming, we're making the hypothesis that that applies to all kissing couples, the population of kissing couples. Now, when he went out, so one of the things he did was he got out his little Reese's Pieces app and did a simulation of 1,000 samples of size 124. So N equals 124. And in his simulation machine, he put that pi is equal to 0.50. So randomly, if we did that, meaning we went into the population and got 124 people and got their proportion of how many of them turned to the right. And let's say we did that the first time and it was like 30.37. And then we did it again and then it was 0.48. And then we did it again and we had another 0.48. And then we got another 124 people, and we got a 0.54. And we did it 1,000 times. We would have constructed this dot plot or histogram here, and it would look like this, if we were assuming that the population proportion is 0.50. This is what the histogram would look like. Now, the central limit theorem does apply in this case because it's a categorical variable. The categorical variable is whether we turn our heads to the right or the left. It is not quantitative, even though we're dealing with these quantities of proportions. These are the proportions of our samples of 124. The underlying variable is whether you turn your head to the right or the left, which is a categorical binary variable. So we're going to see if the central limit theorem applies, which is N times pi has to be greater than or equal to 10. Well, my N is 124, my pi is 0.50, and that's clearly greater than or equal to 10, it's 62. And 1 minus pi would also be 0.50, So the central limit theorem does apply. So we're happy with that. So what it says is that the shape of the distribution will be normal. And in fact, we have a normal shape right here, unimodal and symmetric. The center will be pi, which in this case is 0.50. So in our simulation, sure enough, we have here 0.50 right there in the center. And the spread, well, we would need to calculate that using our central limit theorem standard deviation calculation of the square root of pi times 1 minus pi over n. So looking at a calculator here, I have pi 0.5 times 1 minus 0.5. I'm going to divide that by 124, and I'll take the square root of that. And I find out that my spread would be, we'll call it 0.045. This histogram, it looks like that. I would say that its shape is right, its center is right. The spread, we're not going to calculate that, but we'll do that in the next part of the problem. So I'm pretty happy with using the central limit theorem in this problem. Now, the actual sample of 124 couples that this researcher observed, 80 of them leaned their heads to the right. So out of 124, that is a proportion of 0.645. Well, we just did. And so that is my p hat. P hat equals 0.645. And it's p hat because it's the proportion of the specific sample. So let's take a look at our simulation results and see whether that would make sense. Well, 0.645, that would be like way here, way out here, 0.645. I mean, I didn't get a single one that went out that far when I simulated 1,000 couples of 1,000 samples of 124 couples. So I would say that that's not looking like I'm saying that's kind of casting some doubt on my hypothesis. The z-score of that would be z equals 0.645 minus 0.50, which is the hypothetical proportion center, divided by 0.045, which was our standard deviation, and that comes out to be 3.22. That is a really big standard deviation that is really far from the mean. And if we look at remember our empirical rule, if I go 1, 2, 3, negative 1, 2, 3, between the -3 and +3 standard deviations, that would include 99.7% of all the data. So to get something beyond 3, well, that's like a less than 0.3% chance. It's actually a less than a 0.15% chance. A very, very tiny probability that that would happen. So I would say that casts some doubt on my hypothesis. My hypothesis was that 1/2 of all kissing couples lean to the right. My actual observation of a sample of 124 was that p hat equals 0.645. If my hypothesis is correct, this is a very, very, very unusual result. Not impossible, could happen, but it's making me think it through a little bit more deeply. This leads us to the concept of statistical significance. And you have to kind of think about this. It's like a double negative. Something is statistically significant if it is unlikely to occur due to just random sampling variability. So back here to my picture here, you know, if my actual proportion had been over here, well, let's use a different color, had been over here someplace, or maybe even over here someplace, you know, that's looking like that's within the reason. It could have been randomly sampled. But like way out here, I don't know. Even with a random sample of 1,000 times, we didn't even come close to something like that. This is a statistically significant result. So statistically significant means unlikely to happen with just normal random sampling. Well, let's try a different hypothesis. Let's say that the population proportion turning to the right is 2/3. So we're changing it to pi is equal to 0.67. So I would check my conditions for the central limit theorem, and I can tell you that they will apply, but you should check them anyways. So it will be normally shaped. My center will be 0.67, and my standard deviation will be 0.67 times 1 minus 0.67 divided by 124. Take the square root. So we go 0.67 times 1 minus 0.67, which is 0.33, divided by 124. Take the square root, and I get, well, 0.042. So it's not that far apart from the other one, but let's make our diagram. 1, 2, 3, -1, -2, -3. So I have 0.67 is in the middle, plus 0.042, plus 0.042, plus 0.042. So I got 0.42. So this here is 0.712. So 0.712 plus 0.042 gives me 0.754 plus 0.042 gives me 0.796. And if I go 0.67 minus 0.042 minus 0.042 minus 0.042, on this side I get 0.628, 0.586, 0.544. And now, looking at my actual result of p hat equals 0.645, well, that would be somewhere right in here. And that looks a lot more reasonable to me. I mean, that's like less than 1 standard deviation away from the mean. So I would say that my hypothesis of 2/3 turning their heads to the right is a much better hypothesis than my hypothesis of 1/2 turning their heads to the right.